Good evening, everyone. Today, I will share concepts and ideas in the topic on hybridization and resonance. So in the A-level chemistry syllabus, these are the learning outcomes for this topic. Students should be able to describe SP3 hybridization using the example of ethane, SP2 hybridization in ethene, as well as benzene molecules, and SP hybridization in ethyl molecule. We will also spend time to explain the shape of and bond angles in ethane, ethene, benzene, and ethyl molecules in relation to sigma and pi carbon-carbon bond, and predict the shape and bond angle in molecules similar to those in Objective B, and interpret and use the terminology associated with the organic reactivities, delocalization. So these are the content that we're going to go through today. Okay, what is hybridization? The theory of covalent bond formation via overlapping of atomic orbitals does not always give good agreement with observations. Hybridization is a concept to explain the observed shapes of molecules that is actually determined by experimental study. So consider the electronic configuration of carbon at ground state. Now, to form a covalent bond, an orbital containing one electron is required. These orbitals will overlap to form a covalent bond. Now, carbon in its ground state contains only two singly occupied orbitals. So if you recall the configuration of carbon, okay, so you have two electrons in the 2s orbital and two electrons in the 2p orbitals. All right. Now, there are two singly occupied orbitals. So these are the two singly occupied orbitals, which are the 2p orbital. So by right, carbon should form two covalent bonds because only these two electrons here can form two bonds. But we all know that carbon forms four and not two. So how do you explain that carbon forms four and not two using the electron in box diagram? In order to form four covalent bonds, it means that okay, all the four orbitals are singly occupied. So the electron from 2s must be promoted to the empty 2p orbital in order for four covalent bonds to be formed. So carbon in the excited state. So this will explain why carbon form four covalent bonds. So carbon now has four unpaired electrons and can form four covalent bonds. But the atomic orbitals do not point in the correct direction for bonding. For example, CH4, methane, is tetrahedral with HCH bond angle of 109.5 degrees. But the p orbitals is actually perpendicular to one another. So if we are going to use this to explain the shapes of orbitals, it will be difficult because there's some misalignment. Okay, so p orbitals are perpendicular and should not be 109.5. This is very weird. So how do you explain the 4 CH bond in methane with an angle of 109.5 degrees? We use the hypothetical concept of hybrid orbitals. Now, so we can observe SP3 hybridization of carbon in methane. Structural studies have shown that CH4 is tetrahedral with all the CH bond being of equal bond length and the 4 HCH angles are all 109.5 degrees. This is what we learned in the previous topic. Okay. Okay, but right, one of it should be in 3D. So for this one, we'll expect, okay, it could be this. So this implies that carbon must provide 4 equivalent orbitals for head-on overlap with the 1s orbital from each carbon atom, so that we can form 4 identical CH sigma bonds. Okay, if you recall what is sigma bond in the earlier chapter, okay, the hybrid orbital are orientated in the tetrahedral geometry, which contain a single unpaired electron. What is hybridization then? All right, so the word hybridization keep on coming up, but what it really means? Hybridization is the term applied to the mixing of atomic orbitals in order to generate a set of equivalent orbitals. So the orbitals of one atom that is forming a bond with another will have their atomic orbitals mixed. And the mixing of the orbitals is called hybridization. Now, so we have 4 equivalent hybrid orbitals for carbon generated by mixing one 2s orbital with 3 2p orbitals. This will result in the formation of 4 SP3 hybrid orbitals. Now, so this is the s orbital from the 2s. Then these 3 are the 3p orbitals in different orientations: px, py, and pz. So px is along the x-axis, py along the y-axis, and for pz, the orbitals is along the z-axis. So during hybridization, 4 sp3 hybrid orbitals will be formed. So you have something like this. So the orbitals will mix sp orbitals. P3 because there are 3 p orbitals involved. All right. Now, so the 1s orbital, this 1s orbital belongs to the hydrogen. So what happened is that, what happened is that the 2s orbital and the 3 2p orbitals will mix together in this hybridization process. So you have this. So the 1s orbital and 3p orbitals will hybridize to form 4 equivalent sp3 hybrid orbitals. Okay, the large loops of the hybrid orbital will point towards the corners of the tetrahedron. Okay, so you have the, yep, so the s will mix with them lah. Now, so each of the 4 sp3 hybrid orbitals of carbon will overlap with the 1s orbital of the hydrogen atom to give a tetrahedral methane molecule like this. So look at this diagram. So you have sp3, sp3, sp3. So somehow these 3 orbitals will mix or hybridize. Okay, then you have this 4 orbitals created or formed. Now, So we also look at other examples in NH3 and H2O. So these are the examples of molecules where the central atom is also sp3 hybridized, which include ammonia and water. So sp3 hybridization will result in a tetrahedral electron pair geometry. Just bear that in mind. Let's move on to sp2. Looking at ethene as the example, structural studies have shown that C2H4 is planar with all the CH bond of equal bond length. And the HCH and CCH bonds are 120 degrees. So this is 120, this is 120. Okay, based on structural studies or experimental studies. So this implies that the carbon must provide 3 equivalent orbitals for head-on overlap with the 1s orbital from each hydrogen atom and with the orbital of another carbon atom. The hybrid orbitals will be orientated in a trigonal planar geometry that contain a single unpaired electron. The CH bond in C2H4 are single covalent bond, while the carbon-carbon bond is a double bond between the carbon. So each carbon forms 3 sigma bond, 2 with hydrogen and 1 with carbon, and 1 pi bond. That is the bond in the double bond between the carbon atoms. Each of the carbon atom undergoes SP2 hybridization to generate 3 equivalent SP2 hybrid orbitals for forming 3 sigma bonds. So SP2, you have 3 orbitals undergoes hybridization. But there is one unhybridized 2pz orbital that remains, that doesn't get hybridized. That's why it's sp2 plus a 2pz that is not involved in the hybridization. That will form the pi bond. So during sp2 hybridization, we will have one of the electron here will be still promoted. This one and this one will mix. But this one will remain unhybridized. It will not be involved in the mixing of these 3. So the 2s electron will mix with these 2 to form 2sp2, 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 so 3. And this one is not in the sigma bond, it's the pi bond. So this one is a sigma, while this is the pi bond. So for sp2 hybridization, okay, it looks something like this. So you have the 2pz orbital forms the pi bond here, above and below the plane, side to side. Okay, so sp2, sp2, sp2. Note that the unhybridized p orbital will be perpendicular to the plane containing the sp2 hybridized orbital. Another example of a molecule where the central atom is sp2 will be EF3. Now let's look at the last one, sp hybridization in ethane, the one with the triple bond between the carbon. Structural studies show that C2H2 is linear with the CH bond of equal bond length, and HCC and CCH angles are 180 degrees. So this implies that carbon must provide 2 equivalent orbitals for head-on overlap with the 1s orbital of the H atom and with the orbital of another C atom. Each orbital is orientated in a linear geometry containing a single unpaired electron. The CH bonds in C2H4, or rather C2H2, are single covalent bonds, while the carbon-carbon bond is a triple bond. Now, each carbon forms 2 sigma bonds, one with 1 hydrogen atom and one with the carbon atom. Each of the carbon atom undergoes sp hybridization to generate 2 equivalent sp hybrid orbitals for forming the 2 sigma bond. The two unhybridized 2p orbital will remain to form the two pi bonds. Okay, so you have the hybridization taking place. So what happened is that this and this will have their orbitals mixed, undergoes hybridization to form 2sp, while these two will be unhybridized to form the pi bond. All right, so you have two pi bonds, okay, and two sigma bond. Now, two sigma bond, one sigma bond is between the carbon atoms, the other one is between the C and H here. So one of it come here, the other goes here. Okay, then these two come from here. So this is for triple bond between carbon atoms. Now, the unhybridized p orbitals are still perpendicular to each other, and the line containing the sp hybridized orbital. So in conclusion, when we have SP3 hybridization, this is how you represent the diagram. You have to draw in this way. All right. There are four hybridized orbitals formed for SP3. There is no unhybridized p orbitals. Okay, all are hybridized. And there are four regions of electron density. The geometry around the atom, the central atom will be tetrahedral with 109.5 degrees. For sp2 hybridization, we have three hybridized orbitals, one unhybridized p orbital, three regions of electron density to form an electron pair geometry of trigonal planar, 120 degrees. sp hybridization, we have two hybridized orbitals and two unhybridized p orbital. The regions of electron density is dropped to 2. And the geometry around the atom is linear. Now, so sp hybridized orbital means you have one s and one p. So the hybrid is of two sp orbitals, and the shape is linear. Because there's only one p, so you don't have a 2 here, it's 1 here. But you don't need to write a 1. For sp2, 1s and 2p, so you have 3 sp2, 120 degrees, trigonal planar. And if you have sp3, is 1p, 1s, I apologize, and 3p. So it forms 4 sp3 orbitals of 109.5 degrees, tetrahedral. Now, pause this video to determine the type of hybridization, what each circle atoms is. Okay, now for the first one, there's a double bond between carbon and oxygen. So the carbon atoms here, the hybridization is sp2. Here, there's no double or triple bond, sp3. Here, sp. Here, you have double bond, sp2. Here, you have two double bond. So carbon has actually two pi bond. So it's actually sp. Then here is sp3 also. Yep. Then for N2H4, another example, will be sp3. So the lone pair is considered as one of the region of electron density. So as long as your region of electron density either is a bond or lone pair, doesn't matter, it will still be recognized as one of the region of electron density and determine the type of hybridization then. Yeah, just like ammonia here, it's actually SP3 tetrahedral. I mean, look like tetrahedral, but you cannot say tetrahedral because of the lone pair you learn in BSCPR, right? So it's actually not that, but the hybridization is still SP3 lah. Yeah. Now, the s orbital is actually spherical and the electrons are closer to the nucleus. So when we have sp3, the character of S is 25%, sp2 is about 33, and sp is the highest, 50%. So the more p you have, the less s it will be. The less s character it will be means the electrons are not so close to the nucleus, and we have a situation where the hybrid orbital will be less diffuse. So sp is less diffuse. Which means the more tightly the shared electrons are held by the nuclei, and the more effective is overlap with the orbital of the other atom, and the stronger the bond and shorter its bond length. So moving from ethane to ethene to ethyne, the CH bond strength actually increases. Now, CH bond length decreases from ethane to ethene to ethyne as shown in the table below. So with an increased S character, the orbitals involved will also be different. The bond energy will change. So the SP hybrid orbital should have the highest bond energy and yet the lowest bond length. So these two are opposite to each other. The greater or the longer the bond length, okay, the smaller the bond energy, because the proximity of the shared electrons to the nuclei is further. So weaker the electrostatic force between them. Now try this exercise like at your own time and check your answer. Okay, so for C2 and C3, what is the explanation for the bond length of 0.146 nanometer? Okay, so they are saying that in this molecule, the bond length is even shorter than ethane, which is 0.154. Now, it has to do with the sp and sp3 overlap, which results in greater S character, and the bond is shorter, which means that the bond energy is higher. It's more difficult to break them. Okay. Now, lastly, we talk about resonance. The bonding in some ions and molecules cannot be adequately explained by using just one dot and cross diagram or structural formula. For example, if you look at ozone, there are actually two possible structures of ozone, which suggests that this molecule could be unsymmetrical with one oxygen-oxygen bond shorter than the other. However, when the oxygen-oxygen bond lengths in ozone are measured, both are found to be the same and midway between OO and O double bond O. So what does it mean? Clearly, the resonance structures for these two are not the correct representation. In reality, right, the actual structure of the molecule is a hybrid of them, meaning sometimes it can be this, sometimes it can be this. So it can exist either or. This is what we call resonance hybrid. So in the resonance hybrid, the pi bonding electrons are delocalized over the oxygen atoms via the overlapping of p orbitals of oxygen atoms. So the electrons are delocalized and they also overlap because of the good overlapping of p orbitals of these oxygen atoms in ozone. So the electrons can actually move quite freely between the atoms, all right, along the sigma bond. So these are the various resonance structures of ozone. So this means Okay, it's form a dative bond. Okay, so it can actually, so it's actually a mix between these two. Double bond could be here or here. Okay, and the resonant hybrid, right, is found to be even more stable than any of the resonant structure. Resonant does not mean the species flip-flop back and forth. No, this does not imply this. It does not mean flip-flop. And even you have the reversible sign, it also doesn't imply resonant form. Okay. Now, nitrate ion. Let's look at it. So in this example, we see the resonance structure of nitrate ion. So it can either be this way, and the electron from minus can come down. All right. To form the double bond here. Either that, okay, double bond from, so when this happens, right, sorry, I forget this. So this one will come out. All right. Then to form, what happened here is that after this is formed, okay, this thing can come down and this thing can come up. Yeah, the electrons can move. All right. Now, resonant hybrid contains delocalized electrons with the negative charge spread over the entire ion. So as shown, the N double bond O is not rigidly fixed. All the resonance structure have the same arrangement of nuclide, but differ in the arrangement of electrons. Experimental data again reveals that all the nitrogen-oxygen bond are actually identical and intermediate between NO and N double bond O. Other species that are also resonance stabilized, like carbonate ion or ethanoic ion. All right. Benzene. The carbon atoms are arranged in the form of regular hexagon with all the bond angle corresponding to 120 degrees. So each of the 6 carbon atoms in benzene is SP2 hybridized with the unhybridized p orbital perpendicular to the plane. Benzene has the bond structure formula as shown. So both structure A and B shows that of the 6 carbon-carbon bonds, 3 are single bond while 3 are double bond. The bond length of CC single bond is longer than that of CC double bond. However, experimentally, it is found that all CC bond length in benzene is actually equal, and the bond length is intermediate between single and the double bond, based on experimental data. The two structures A and B are equivalent, and they are known as resonance structures. Okay. Neither of them is an accurate representation, but each contribute to the actual structure. Okay, the real molecule will be described as an average of the two resonant forms. That's why when you represent benzene ring, you have to draw in this way to demonstrate the understanding of resonance. So structure C is known as a resonance hybrid of A and B. The resonance hybrid will be more stable than any of it. So the resonance hybrid is more stable because of the delocalization of electrons. So the 6 C atoms in the benzene ring are SP2 hybridized. Okay, SP2 because of the double bond. So each carbon atom still has an unhybridized p orbital containing 1 electron. So the 6 unhybridized p orbital in a benzene will overlap. So when they overlap, So whenever there's good overlapping, the electrons will be allowed to interact with each other, and this form a plane of delocalized pi electron above and below the plane of the benzene ring. Okay, let's do a revisit of the structure of graphite and diamond with a different perspective this time around, looking at hybridization. So looking at diamond, now we can see that we can also describe this as SP3 hybridized for each carbon atom, where they covalently bonded to 4 other carbon atoms and arranged in a tetrahedral manner. This tetrahedral arrangement is repeated throughout the whole molecule to give rise to interlocking hexagonal units. Okay, so that the resultant structure, hexagonal is here, can you see it? Yep. So this hexagonal units, right, is interlocking and it will be extremely strong and rigid. And you also notice that diamond does not have any delocalized electrons, which means it is an electrical insulator since it's made up of neutral atoms. As for graphite, okay, it has a layer structure making out of planes of interconnected hexagonal rings of carbon atoms. In this case, right, we have the SP2 hybridized for each carbon atom here. So there's only 3 sigma bonds formed between with these 3 carbon atoms. Okay, SP2. The electron pair geometry is trigonal planar with a bond angle of 120 degrees. So each carbon actually still has an unhybridized p orbital, which contains a single electron. So same thing, the p orbital of the carbon atom will overlap collaterally with the p orbitals. Let me see something. The p orbital of one carbon atom will overlap collaterally with the p orbital of the immediate neighbor to form an extended pi electron cloud above and below the plane that contain the carbon atoms. And the pi electrons are delocalized over the whole layer. So they are delocalized along the layer, which makes graphite an electrical conductor. So the pi electrons, right, which are delocalized within each layer are only able to conduct electricity parallel to the layer. So there is no way they can conduct between the layers. It's along the layers. Now I'm going to skip this. That's it for today. So I hope, okay, so this is just an exercise to complete the understanding on this section. So how do you explain why graphite has a higher melting point than diamond? Yes, strangely, diamond loses to graphite in terms of melting point. So the reason is this. Okay, both of them are giant covalent structure. And when we melt, then we need to break the covalent bond between the carbon atoms. And in diamond, the carbon atoms are SP3 hybridized. But in graphite, the carbon atoms are SP2 hybridized. So that is the key difference in comparing their melting point. Now, the hybrid orbital of carbon atoms in graphite has higher S character than diamond. So they are less diffuse, and the overlapping of the SP2 hybrid orbitals is actually more effective than the one in diamond, which is SP3. So SP2, right, has better overlapping, leading to less diffuse. And the p orbital that's unhybridized in graphite has to do also. So the p orbital of one carbon atom will overlap collaterally with the p orbital of its immediate neighbor. So there's actually additional electron density between the carbon atoms. And this will actually strengthen the CC bonds, making the melting point harder, because when the CC bond is strengthened, then more energy is required to break this. Therefore, graphite actually has a higher melting point, looking at SP3 versus SP2 hybridization. Okay, and now, so that's it for today. It's a short lesson. So do take some time to revise this important topic. Thank you.